Hello, it's Mr. Norris, and we're going to begin our unit on probability now. What you may find about this unit is it's less involved in computation, perhaps more than any other unit that you've done in this course. There's not a lot of meticulous work that you have to do, but it definitely does make you think. So let's review what you probably already know about probability. So let's think about the classic situation of flipping a coin. So the chance that you land on heads would be 1/2. So I'm going to put 1/2 representing that probability. Now, how would we write that? Well, typically we designate a letter to go with a particular event. So we really have two events going on here. So our events are either we land on heads or we land on tails. We designate a probability function that we typically write when we express some kind of probability. So I might say that the probability P of some event tails is going to equal 1/2. This does not mean P times T. This simply means the probability of getting tails is equal to 1/2. So we should also note some additional vocabulary that you want to be aware of. So first of all, we call the top part of our fraction, the numerator, the number of successes. A success is a situation where we get the event that we established in our function. So in this case, there was a 1/2 chance that we got tails. So we're going to put that this is our number of successes up here. And on the bottom, we always put our total number of outcomes. So if somebody asks you what is probability in its most basic forms, well, if you give somebody a probability, you're talking about the ratio of successes to the total number of outcomes. You should also be aware that you're going to see probability expressed in different forms. So you saw it as a fraction up there. You might see it as a decimal, 0.50, or you might see it as a percentage, 50%. This is probably the most basic case that we can think of with heads and tails. There are only two possible outcomes, so we're going to look at something a bit more complicated in our next slide. Let's consider a case where maybe there was some party, room full of people, and 100 of them were from Raleigh, and 40 of them were from Chapel Hill, and 60 of them were from Durham. So let's go ahead and use our probability notation. So let's say that the chance that you're from Raleigh we're going to represent as R, so that's going to be our event that we're talking about. So the probability that you're from Raleigh is going to be 100 over what? Well, there are 100 people from Raleigh, but I know overall if I add these up, 100 plus 40 is 140, 140 plus 60 is 200. So I have to think about the number of successes that I'm from Raleigh is 100, but the total number of possible outcomes is 200. Put more simply, if I'm in a room full of 200 people, there's going to be 100 of them from Raleigh, so I have a 100 in 200 chance of randomly picking someone from Raleigh. So I can write that in decimal form. I can do that as 0.5, or I can think about that as 50%. Okay? Let's think about the other one. So let's think about the probability that we're from Chapel Hill. So maybe I'll just put the probability of C. Well, that's going to be 40 over 200. If you have a calculator handy, if you struggle with reducing fractions or converting fractions to decimals, you can always divide 200 into 40. Okay? So anyway, if you need to do that, that's perfectly fine. So 40 over 20 can be reduced to 1/5. And we could write that as 0.2 or 20%. Okay, and let's finally find the probability that you're from Durham. So maybe I'll do red for that. So the probability that you're from Durham is going to be 60 over 200. Okay, that can be reduced to 3 over 10, which I know is 0.3, which I can also write as 30%. So The reason I gave you this example is, first of all, I want you to realize that probability can be used in a situation where there's more than two possible outcomes. The coin example was alright, but we wanted to look at something where there's more than two outcomes. Additionally, we want to look at this idea, again, that we're using our probability notation, we're thinking about writing this as a fraction, writing our probability as a fraction, also as a decimal, also as a percentage. There's another important idea here that you intuitively know, but we need to spell out very specifically, and that's that your percentages cannot exceed 100%. So if I have 50%, oops, didn't mean to do that. If I have 50% of the people, that's representing the fact that there are 50% of people in the room from Raleigh, and then I'm adding the 20% from Chapel Hill, and then I'm adding the 30% from Durham, I'll get up to 100%, which is precisely what I wanted. We can't reasonably talk about 110% or 120% of something. We use it in expressions and in speech, but mathematically, we don't really have a firm concept of what it means to have 110% of something. If you get percentages that add up to under 100 or over 100, then you've most likely done something wrong. Let's use this example to illustrate one more idea. So maybe I'll take this, shrink it a bit, and put it to the side. And we're going to introduce the idea of a complement. So I think I'm going to use green for this. So we're going to do the probability that you are not from Durham. So the probability that you're not from Durham, we write as D, C, and close brackets. This C indicates the complement, which means the chance that you are not someone who lives in Durham. So let's think about what that means. So there's a formula that tells us that if you take 100% of something and subtract, in this case, P of D, you should ultimately get the probability of D complement. So the idea is that if you take 100% minus the chance that you are from Durham, so let's do that. We have 100%. We take away the chance that you are from Durham, which is a 30% chance, and we get out 70%. So what that practically means is that there's a 70% chance that if I randomly choose somebody in that room, I'm going to choose someone who's not from Durham. And this intuitively makes sense. Think about the two main kinds of weather we think about. We think about, is it going to rain or is it not going to rain? So if the weatherman tells you that there's a 70% chance that it's going to rain, clearly there's a 30% chance that it's not going to rain. In the same way, if there's a 30% chance that you're from Durham and that I randomly pick out someone in this room from Durham, then there's clearly a 70% chance that I'm going to pick someone who's not from Durham. So there's one more additional notation note we need to make here. So we used percentages in this case, but if we were using decimals, we might have to make it a little bit different. We might have to say the number 1 minus 0.3, and that would get us to 0.7. Whether we use percentages or whether we use decimals, it's still hitting on the same idea. It's just a matter of what we prefer to use. Okay, so in this section, we've gone over a little bit more about probability notation. We've gotten the idea that things should always add up to 100%. And we've discussed the notion of the complement, mainly this idea that the probability of something not happening is equal to 100% minus the chance that it does happen. So we're going to look at another example with heads and tails. So this notion of flipping a coin. But in the past, we've only looked at single events. So what's the probability you land on heads? What's the probability you land on tails? What's the probability that if I'm in a room with people from across the triangle, that I randomly pick somebody from Raleigh? But what about if I wanted to look at the probability of multiple events occurring? For example, the probability of landing on heads 3 times in a row, or the probability of landing on tails at least twice, something like that. So in some cases, you're able to write out the sample space for all possible events. So let's look at what we mean by sample space. So the problem that we're going to consider is all the possible outcomes that you can have if you flip a coin 3 times. Okay, So let's try that. So I can get heads, heads, and heads. So H, H, H. I can get H, H, T. H, T, H. And then H, T, T. So I've exhausted all my cases where H appears first. Okay, let's consider the case where I have tails first. So I could do, oops, didn't mean to do that. I could do tails, heads, heads, THT, and then TTH, and finally T 3 times, so 3 tails in a row. So what I've done here is I've actually outlined my sample space. My sample space is simply my set of all possible outcomes. Okay, so we're going to take this and zoom out a bit. So let's think about two events. Let's say the probability of getting tails twice in a row. So let's go ahead and put it out there as maybe the probability of T and T. Okay? So there's a formula that tells us that when we're dealing with multiple events, specifically the state where we have some event and some event, we simply multiply the probability of those single events together. So let's see what we mean by that. So we're talking about the probability of landing on tails times the probability of landing on tails. We could simplify that to the probability of landing on tails. You know that's 1/2. Again, we're going to put another 1/2 here. So the probability of landing on tails twice is simply 1/2 times 1/2, which we end up with 1/4. We're going to look at another example here. So we're going to take everything at the top and we're going to use it, but now we're going to ask ourselves the question, what's the chance of arriving at least one tail? So if I flip a coin 3 times, what's the probability that I get at least one tail? This is going to be a kind of problem where we can use the idea of the complement of an event, just as we did in our last example. So let's call the probability of getting at least one tail maybe A. So that event, that chance of getting at least one tail, is going to be A. So the probability of A is equal to 1 minus the probability that A does not happen. Oops, didn't mean to do that. It's equal to 1 minus the probability that A does not happen. So in other words, the chance that we get at least one tail is equal to 100% minus the chance that we don't get at least one tail. And the probability that we don't get at least one tail is actually just the probability that we get all heads. So think about that. If we don't get at least one tail, then we must have gotten heads 3 times in a row. So this is going to be equal to 1 minus the probability of heads times itself 3 times. So in other words, 1/2 times 1/2 times 1/2. And from that we get 1 minus 1/8. I'm going to zoom out a little bit because I'm running out of room. Okay, so we get 1 minus 1/8, and that just becomes 7/8. So if we're stepping back from this, there's a 7 in 8 chance that we get at least one heads. And we got this from this notion of the complement, that the probability of something happening is equal to 100% minus the probability that it does not happen. This problem also introduced us to the notion of saying that I'll consider the probability of at least this many successful events happening. In a lot of the problems that you get on probability, you're going to see the word at least. What's the chance that at least this many successes occur in a total number of outcomes? And just strategy-wise, typically when they're asking you to think about the word at least, they're asking you the phrase at least, they're asking you to think about the notion of the complement of some event. Okay, after this we're going to look at one more quick slide. And with that point, we will conclude the video. So in the last slide, you looked at the probability of something happening in the sense that we had like some A and some B. So probability of A and B. And from that you realize that we just multiply the probability of A times the probability of B to get that result. Okay? But we also have to consider the case where we're dealing with OR. So let's talk about that. So let's consider a situation where we have a bag of 6 green marbles. Kind of ugly, sorry about that. A bag of 6 green marbles and 8 blue marbles and 4 purple marbles. And I'm asked, what's the probability that I get green or that I get purple? Okay, so let's think about that a little bit more. So to do that, I have to add those two probabilities together. So I'm looking at the probability of green plus the probability of purple. So I'm going to do little p to indicate the difference between p, the probability function, and p, the event purple. Okay, so the probability that you get green, let's think about that. So there's, let's see, 14 plus 4, we're looking at 18 marbles in this bag of marbles. And there are 6 that are green. So we're looking at 6 out of 18 marbles that are green, plus 4 out of 18 marbles that are purple. And so from that we get a probability of 10 out of 18. Oops, a little bit too small. Probability of 10 out of 18, chance that you're looking at getting a green marble or a purple marble. So to review, in this video we discussed probability. So the probability that some event happens is ultimately the number of successes over the total number of outcomes, or out of possible outcomes. We learned the general rule that if you have the probability of A and B, that you should multiply the probability of A times the probability of B. We learned that if you have the probability of A or B, then you should look at the probability of A plus the probability of B. We've also discussed this idea of sample space. And the sample space is just a list of all of your possible outcomes. So in the case where I was trying to write the sample space for flipping a coin, maybe I call heads H, tails T. My sample space is just H and T. Has 2 elements in it, 2 possibilities. And finally, we've discussed this idea of the complement. So if we have, oops, sorry about that. If we have the probability of A complement happening, in other words, the probability that A does not happen, then we can look at that as 1 minus the probability that it does happen. In the same way, if we want to look at the probability of A occurring, we can look at 1 minus the probability that it does not occur. Okay, so with that review, we will conclude this video.